Hello, physical science students. Let's do ionizing power and penetrating power. Now, when we were talking about radiation, recognize that radiation is the transmitting of energies from one place to another, and so it's a big area that includes a lot of things, and we're looking at a tiny little bit of radiation. We're looking at radioactivity, and we're looking at the alpha, beta and gamma radiation with it, and we have called it ionizing radiation. So just recapping what ionizing radiation means, it's the formation of ions, and so alpha, beta and gamma radiation can form the formation of ions. What's an ion again? Well, if you have an atom, any element, it's got its nucleus, and then it's got its number of electrons around it. Number of electrons equals the number of protons, and so overall the atom is neutral. And the formation of an ion is when that atom either gains or loses electrons, and so it's no longer neutral. And that's what ionizing radiation can do. It can cause the formation of ions. And if we ranked it, alpha radiation has the greatest ionizing power, beta is sitting in the middle, and gamma is the least ionizing. Now, how do they do it? Well, the simplest method is that the ionizing, the alpha or beta particle comes in, gets really close to an electron, and either knocks it out or absorbs the electron. In the case of alpha radiation, remember alpha radiation is a helium nucleus, so overall it's got a +2 charge. It's actually very attractive to this electron, so if it interacts very closely with it, it just sucks it to itself, because ultimately the alpha particle wants to gain 2 electrons through this process to become neutral. Whereas the beta particle, being an electron itself, all it has to do is get really close to the electron in the shell, and the 2 negative charges repel each other with sufficient force to cause them to shoot off in opposite directions, and that means that this electron is no longer in the shell, and overall this atom then becomes positive. Got that? Now, this table here is off your information sheet, and so you don't have to memorize all this information. I thought it was time to introduce you to it. And so we have alpha, beta, gamma, neutron and proton as our particles, and we have the nature of radiation, electrical charge, mass, distance travelled in air, which we're going to talk about shortly, and stop by, which we're going to talk about shortly as well. Now, why have I introduced this here? Because it helps explain the ionizing power. If we look at the alpha, now this was the greatest, and so in terms of ionizing power, we can draw a wavy thing. We can go increasing in that direction from here. Okay, so gamma least, beta alpha. Now, why is that? Well, gamma is not very ionizing because it has no charge, and even though it's traveling very, very fast, it doesn't really interact with things. It can get absorbed by things and cause some changes, but it doesn't really cause ionization. In some cases it does, but most of the gamma rays interact with you in a different way from ionization. Now, the beta particle is your middle ionizer because even though it's small, so it's only an electron, it has a charge, and that charge means that it's actually repulsive to other electrons. So if it gets close enough to other electrons that are actually in orbitals around a nucleus, it can cause them to be repelled. And lastly, we've got the alpha particle, and it's this +2 charge that makes it very attractive to electrons, and so effectively it can steal electrons from other atoms. And when we talk about why radiation is potentially harmful to organic bodies like ourselves, it relates pretty much to the ionizing power and how the human body or any living organism absorbs that ionizing or the formation of ions. Now, here we've got a little list of distance travelled in air, so you don't have to memorize this, and we're going to do a prac that should hopefully reinforce this. and we've got a little diagram coming up here soon. Now the information about the neutron and the proton is pretty much there. You don't have to remember the symbols. Remembering a proton is just a hydrogen nucleus. And in terms of penetration, because stop by is another way of just saying the penetrating power, the neutron obviously goes a lot further than the proton, which isn't shown in this next diagram. Let's see if I can get that up. So what we're trying to show here is we've got a block of some sort of absorber, and we're firing alpha, beta and gamma radiation to it, and these dots represent the sites of ionization. So where the radiation is interacting with the atoms and causing the gaining or the losing of electrons. And you can see that alpha is absorbed very quickly, but there's lots of sites of ionization. And we're assuming that we're sending in equal amounts of alpha, beta and gamma into here. The beta penetrates more. There's a lot less ionization because the electron is sometimes just absorbed without any ionizing occur, because there's lots of free electrons in going around in most bodies. There's what we call a sea of electrons, and so these electrons, the ones that aren't showing ionization, are just becoming part of the sea of electrons. And the gamma radiation, you can see a few spots here going much more in terms of penetration. Another diagram here where you've got all these atoms, little black dots, and the dots, white dots, represent where ionization has occurred. And lastly, another figure here where we've got alpha particles here on the top, gamma rays here, which is a bit strange, they should have put beta there, and then beta particles down here. And first of all, the alpha particles stopped by a piece of paper. For some reason they didn't show the beta particle going through the paper, but most of the beta particle would go through a piece of paper, but is then stopped by a piece of aluminium, probably a little bit thinner than that, whereas the gamma ray goes through the paper, through the aluminium, through the person, and stopped by a thickness of lead and concrete. Now this is why we, when we store our radioactive samples or our traces or our sources at Newstead, we put them in lead. There you go, lead casing, and that pretty much stops most radiation. And if you go anywhere where they use radioactivity or radioactive samples, lead is the main thing they use to absorb nearly all the radiation. Alright, so that's enough about that. We should be able to do a prac here, and what we'll do in the prac is actually the whole class will put their results together, and we'll hopefully confirm this sort of thing. But we won't be firing radiation through ourselves. Not allowed to do that. Cheerio! Next video is, of course, half-life. Forgot to say. Cheerio!